Time for some practice involving partial derivatives. Something which is actually very similar to just normal derivatives. The only thing that happens is keep track of which variable you're taking the derivative with respect to and which ones are constants. And once you get the hang of it, it's not so bad. But how do you get the hang of it? You practice. And the more you practice, the more second nature things become. So do as many problems as you can. If you're following along with the video, make use of the pause button. See a problem? Try it out yourself first and see how far you can get. And if you ever need help, I'm here. Just unpause me and we can work on it together. Well, let's begin. All right, our first problem. Find all first order partial derivatives for g of u vw equals u squared e to the v plus 2w. A nice little warm-up. And this is just a reminder, look, you can have more than two variables. You could have 3 or 7 or 20, any number you want. Same processes work. Now, what's our notation? Well, it's similar, right? We have our three variables, u, v, w. So we say, okay, g sub u, which we can think of taking g sub u is really just a shorthand way of saying we're taking the derivative of g with respect to the first variable. And right now we're calling our first variable u. Of course, we could have called it something else, but for now it's being called u. So taking the derivative of g with respect to what's happening when we vary the first entry. Well, okay, that's not so bad. That says the u is the variable, and this other stuff is a constant. Derivative of u squared, 2u. And then this other stuff is a constant, so it's still there. All right, g, v. Okay, well, now the v varies. That means the u and the w are the constants. So we have our constant, u squared, and the derivative of e to the v plus 2w. Well, e to the v plus 2w, because we're taking the derivative of e to something, it's e to something, times the derivative of v plus 2w with respect to v, which is 1. All right, so that's that. And g sub w, u squared, great, e to the v plus 2w, right? Now why u squared? Because it's a constant. The derivative of e to something is e to something times the derivative of the inside, the something. We're taking derivative with respect to w, and therefore the derivative of v plus 2w with respect to w is 2. And we're done. See, it's really just saying take the derivatives like you used to. It's the same principles in play. That's wonderful. So we really don't have to learn new ideas. It's just practice in using our old ideas, which is great. Good. All right. Well, let's try some more. Our next problem. Find all second order partial derivatives of g of xyz equals z cubed e to the x plus natural log of x squared plus 1 times y cubed. Cool. All right. Now, before we get too far, how many second order partial derivatives will we have? It's not such a trivial thing to ask. There's two answers, depending upon how you look at it. One could say there's 9. Now, where does 9 come from? We have 3 variables, and so we could take the derivative with respect to any 3 in the first time and any 3 in the second time. And so 3 times 3 gives us 9. But you could also say that there's 6. Now, where does 6 come from? Well, the 6 comes from the saying, we have this notion that it shouldn't matter which order we take derivatives. So if I take derivative with respect to x and then y, that's the same as y and then x. So we can save ourselves some work and say, hey, let's cut down. So in particular, we could say, well, what would our second derivatives look like? We'll make some notes here. There would be a gxx, a gyy, and a gzz. Those would all be there. And then you'd have things like gxy, which is the same as gyx. See, that's why you get the sort of double counting. And similar, gxz, which is gzx, and we'll say the last one, gyz, which is gzy. So those are all of our second order partial derivatives. So that's what we have to find. Well, how to begin? Well, let's make an observation. We're going to have to take a lot of derivatives, but before you start taking derivatives, you should always ask the question, can I simplify the function? Another way to think about it, have they really given me the function in the best form possible? Now you might say, the function is the function. Why should we care about the form it's been given in? Well, we should care because perhaps a different form will make it easier to work with. Think about this function. What do we see? Well, the z cubed e to the x, not much you can do there. But the next term, log. Log has some beautiful properties. See, log is a great way to pull apart multiplication, which is why we like working with logs, as it helps turn multiplication into addition. And addition is a much easier thing to work with when it comes to taking derivatives. In particular, we could write this as z cubed e to the x plus log x squared plus 1 plus 3 natural log of y. So in other words, pull apart the x squared plus 1 and the y cubed. Now you're probably thinking, wait, y cubed? You wrote 3 natural log of y. Well, because log of y cubed, the 3 comes down. So that's why it becomes 3 natural log y. And now, because we've pulled it apart, it'll be a little bit easier. I'm not going to say trivial, but I will say easier. So let's take our partial derivatives using this new way to write. Because we have to start with our first order partial derivatives. So g sub x. Okay, it shows up x in 2 places. That term will completely go away. So we see that the first term, well, it's the z cubed is a constant, and the derivative of e to the x is e to the x. Log of x squared plus 1. Well, that would be 1 over x squared plus 1 times 2x. All right. And then the 3 log y, since there's no x, it goes away. Now to help us in our next round, let's just note that 2x over x squared plus 1 is the same as 2x times x squared plus 1 to the minus 1. All right, g sub y. What's that one? Well, g sub y, we go through and say, there's no y. There's no y. There's one y. The derivative of natural log y with respect to y would be 1 over y. Or if you like, you can write that as 3y to the minus 1 power. Okay, great. We're doing wonderful. And g sub z, what would that be? There's only one z. Those terms are going to go away because they're going to be treated like constants when we take the derivative with respect to z. Derivative of z cubed is 3z squared, and the e to the x is a constant with respect to z, so it just comes down as a constant. All right, so there's our function. We simplified our function. Now we have our derivatives, and now we can talk about our second derivatives. Okay, so by the way, really second order just means taking 2. No worries. So for gxx, we go through and say, okay, well, there's an x in that term, so the derivative of z cubed e to the x. Well, z cubed, that's our constant, e to the x. Here, well, there's x's in 2 places, so we'll do a product rule. Derivative of 2x will be 2. And we really should say derivative of 2x with respect to x. Oftentimes I'll forget to say that out loud, and I apologize, but it's we're at least thinking it, right? We're at least thinking it, right? Good. That's the key. That's the key. Okay. So that's derivative of the first times the second plus the first, 2x, times the derivative of the second. Well, derivative with respect to x, so negative 1, x squared plus 1 to the negative 2 times root of the inside, 2x. They didn't say we have to simplify, so we won't. We'll just leave it like that. G, y, y, well, derivative of 3 times y to the minus 1, well, is minus 3 y to the minus 2. All right, that's not so bad. G, z, z, well, there's only a single z, derivative of 3z squared, 6z, and of course the e to the x is there as a constant. Okay, how about gxy or gyx? It doesn't matter, right? When you look at g sub x, there's no y. Look at g sub y, there's no x. So it goes away. And therefore, we get 0. How about gxz? Okay, so we can come either take the derivative of g sub x with respect to z, or g sub z with respect to x. Probably it's really easy here, right? 3z squared is a constant. Derivative of e to the x with respect to x is e to the x. So we end up with 3z squared e to the x. And how about gyz or gzy? Well, it doesn't matter, right? Gz, there's no y. G sub y, there's no z. And so we get 0. And we're done. There they are. All the second order partial derivatives. Wow. Great. Great. And you're probably thinking, that's crazy. And think about like third order and fourth order. Are we ever going to have to do these kinds of things? There will be a use for second order partial derivatives coming up. So we will definitely talk about second order. We tend not to go much further than that in this course. Other than in theory, we can. But in practice, we usually stop at second order. All right, good. Well, let's try another one. Another problem. Determine all the values of b so that the function e to the power 2x minus by satisfies the following relationship. 2fxx plus fxy equals fyy. So in other words, we have an equation that involves partial derivatives. So we're kind of trying to solve a partial differential equation. But we've been given a big hint saying it kind of looks like this. We just really need to narrow it down to make sure we have it just right. So, well, what do? Well, we kind of know what we're shooting for. We're looking for these partial derivatives. So let's figure out what the partial derivatives are. Remember, b is a number. We just don't know what it is. But in terms of derivatives, we treat it like a constant. So our function f of xy is e to the 2x minus by. So we need to get fxx, fxy, fyy. So it really says we're after all of our second order partial derivatives. That's okay. No problem. So f sub x, well, you'll notice here it's e to something. So you just have to take the derivative of something and multiply that. The derivative of 2x minus by with respect to x would be a 2. So it's 2 e to the 2x minus by. F sub y of xy, well, again, it's e to something. So it's e to that something times by the derivative of the inside with respect to y, which would be minus b. F xx, because we need that one. All right, we'll go ahead and write it all out. Xy. Okay, it's constant. E to the 2x minus by, derivative of that. E to the 2x minus by times the derivative of the inside with respect to x, which brings down another 2. So that makes 4. E to the 2x minus by. Fxy. Well, what do we see? Well, we start fx, take the derivative with respect to y. Or you could start with fy, take the derivative with respect to x. you'll get the same answer either way. And when we do that, well, say f sub x, we take it with respect to y, there's the 2, and the root of e to the 2x minus by, e to 2x minus by, times by the derivative of 2x minus by with respect to y, which is a negative b. So minus 2b. And anything else? Oh yeah, we need fyy. fyy of xy. Well, there's a minus b already. When you take the derivative here, e to the 2x minus by, you'll bring down another minus b because you have to multiply by the derivative of that inside with respect to y, which will leave us with a b squared, e to the 2x minus by. All right, so those are all of our second derivatives that we need to figure out. Okay, so put it all together, and we have the following. We have 2 times fxx. So that would be 8 e to the 2x minus by. So this is our 2fxx plus fxy, which would be a minus 2b e to the 2x minus by. And this is our, again, fxy is equal to, on the other side, we have fyy, so that's b squared, e to the 2x minus by. So there's fyy. Okay, so we're just plugging in. Now, what do we want to do? Say, look, they all have something in common. Let's cancel. Can we cancel? So what are we canceling? The e to the 2x minus by. That should be our candidate. Are we allowed to do it? Why should we be nervous? And why are we okay? Okay, first off, are we allowed to do it? Yes, we are allowed to do it. So we can divide through by e to the 2x minus by and cancel. Why should we have been nervous? Well, whenever you're canceling, you always have to be a little bit nervous because you have to ask yourself the question, am I canceling a 0? If the thing I'm canceling could potentially be 0, I have the possibility, the potential that I've lost a solution. In other words, if you divide to cancel and when you're dividing by 0, you're doing something which is a really bad sin in algebra because we've been told, don't divide by 0. That's really, really bad. So why are we okay? And the answer is we have e to something. E to something is never 0. It's always a positive value. So it's okay for us to divide out to cancel. So what's left? Well, what's left is we say, look, we need to have 8 minus 2b equals b squared. That looks a lot like a quadratic because it's a quadratic. So another way to say that is b squared plus 2b minus 8 equals 0. Well, that looks like it factors. Let's see. We need two things that multiply to negative 8, but add to give us 4. Well, there's not a lot of ways to break 8 apart. There's 1 and 8. That's not going to work. 2 and 4. Well, notice it's a negative 8, so it's like negative 2 and 4, or positive 2 and negative 4. But it looks like if I make it a plus 4 and a minus 2, that seems like it should work. Let's check. B squared, that's good, minus 2b plus 4b gives us 2b. Or is it not 2b? No, it is 2b, and then minus 8. Cool, so it factors, and now we're in our lovely situation. A bunch of stuff multiplies, we get 0 out, something must be 0. So we come to the conclusion that b is negative 4 or b is positive 2. So it turns out there are two values that work. And those are the two values. Okay, cool, fun stuff. Well, let's try one more problem. So here we go. Given that z equals, okay, so there's a lot of stuff here. There's actually, let's think about what we have. We have y sine of 2x, seems okay. 1 plus x squared to the power sine of x times e to the x squared, which seems really like, ugh. And then we have this cosine of x, arctangent y to the 4th plus 1, log of y to the 6th plus 137. Yeah, okay. And what are we looking for? We're looking for the second order partial derivative, partial squared z, partial x, partial y at 0, 1. All right, cool. Well, this should be interesting. Okay, a couple of things. You'll notice we didn't write f of xy, we wrote z. That's perfectly okay, no problem. Oftentimes we'll just say z equals, and we say, okay, whatever that z equals, that's our function of x and y. So this partial squared z, if you're not comfortable with that, you can say, well, call this whole thing f of xy, and then you have partial squared f. Whatever makes you comfortable. All right, and so what do we need to do? Well, we could, of course, take the second order derivative and plug in, but I think it would take a while, and it probably would take more than a page to write that down. So what can we do instead? Well, there's a couple of things. There's sort of 2 or 3 nice ideas. So let's start with one simple thing to observe, which is we're talking about derivatives, and we have plus signs. So whenever you see things being added, it says, hey, let's take it and break it into smaller parts. So instead of trying to think of this as one big thing, let's think of it as 3 small things. And so there's the y sine of 2x. That's one piece. There's the 1 plus x squared sine of x, e to the x squared. And then there's this last piece. And for each one, we can think about what should we do and what's the right way to proceed. Now, that's one idea. The other idea is to say, hey, when we're working with these mixed derivatives, I can take it in any order. Okay, that's idea number 2. So another way to say that is if I'm looking for partial squared z, partial x, partial y at 0, 1, it's the same as partial squared z, partial y, partial x at 0, 1. So choose to take things in a convenient order. There's one more idea, but we're going to hold off until we get to the third part to talk about it. And then we're going to be like, I see. Okay, so let's start with number 1. So for number 1, we say, look, that's a really simple function, no big surprises. So what are we after? We're taking the second derivative with respect to x and y of this thing, y sine of 2x. Well, that's really saying take the derivative with respect to x of the derivative with respect to y of y sine of 2x. That's just what the notation means, just written out very explicitly. And so we say, look, the first derivative, piece of cake. So when I take derivative of that with respect to y, well, the sine of 2x is a constant, and then the derivative of y is 1. So that's the derivative with respect to x of sine of 2x. And that derivative, well, that's going to be 2 cosine 2x. The derivative of sine is cosine. Chain rule, bring a 2 out in front. Okay, now we take this and we say at 0, 1, which means the way we interpret this is x equals 0, y equals 1, we get 2. So our contribution from this piece will be 2. We still have 2 more pieces to go. But, progress. Progress. Okay, so let's try another part. Let's do part 2. So what do we see in part 2? Well, if we do this expression here, we'll notice something very quick. What do you see is not there? Well, while it looks complicated with respect to x, notice that what we do is we're saying, hey, first you should be taking derivative with respect to y. And there is no y. So what does that become? Well, if there's no y, that means it doesn't change with respect to y, which means we get 0. And of course, excuse me, and of course, once the inside is 0, the next layer, the derivative will also be 0, and so we get 0. Well, okay, whew, nice. And at 0, 1, this will get 0. So now we're 2/3 the way done. Now, what comes next? Okay, our next layer, well, might be our most interesting one. Layer 3. So, here we go. Let's talk about partial squared. Well, actually, let's just save ourselves some notation here. You take the derivative. What do we have? The derivative with respect to this. Derivative with respect to y looks really unpleasant. Derivative with respect to x, not so bad. So let's swap the order. See, that's what this little fact here says. You can change the order that you take derivatives in. You'll still get the same at the end. So let's do that. Let's do a little switcheroo. Okay, so instead of taking derivative of x after you took derivative of y, you're going to take the derivative of y after you took a derivative of x. Now, at this point, you're probably thinking, that's not looking that much more promising. But we still have one more trick up our sleeve. Okay. Don't worry. They're big sleeves. We have plenty of tricks. Arctangent y to the 4th plus 1. Oh my gosh. Look at this crazy expression. Crazy, crazy expression. So that's the partial derivative with respect to y of negative sine of x, because derivative of cosine is negative sine, and the rest of this is just a constant. Now, what's the other idea? What's the other piece that'll let us finish without a lot of work? The last sort of missing ingredient is to say, oh, wait a second. We're doing an evaluation. So whenever you're doing an evaluation, you start to think in the back of your mind, okay, can we evaluate early? Whoops, evaluate, there we go. Now, sometimes the answer is no. You have to say, I have to wait until a certain point. When is the right point? Well, the right point is whenever I don't need the information that gets lost. Because when you evaluate a function, you reduce it from a function to a number. And you have to say, well, do I need to do something with the function, or is it okay if I just have the number? As a rule of thumb, if I have to take a derivative, I still need the function. If I don't need to take the derivative, and we're talking about differentiation problems, well, then I'm good to go. I cannot evaluate at the very beginning because I need to take derivatives with both respect to x and y. But after I've done one layer of derivatives, I can say, oh, hey, now I don't need to do any more derivatives with respect to whatever I did in my first layer. See, I took the inside with the derivative with respect to x. And I say, I don't need to take any more derivatives with respect to x. So we say, okay, evaluate first. So we're going to evaluate at our choice, x equals 0, because that's where we're after. We're at the point 0, 1. And what happens when you plug 0 in? Well, you get sine of 0, which is 0, times all this other stuff, but it's 0 times stuff is 0. So this last piece says, hey, I just now need to figure out what's the derivative with respect to y of 0, and that's 0. So I've evaluated already at x equals 0. Now we have to evaluate this at y equals 1. Well, we're going to get 0 out. So this is one of our, hey, be careful and pay attention. It's possible for you to do an evaluation early. But generally speaking, if you're taking multiple derivatives, you should always say, let me take derivatives in the order that makes it easiest for me to work with. So what do we get? We got a 2, a 0, and a 0. So we put it all together, and we say, well, 2 plus 0 gives us final answer of 2. And that's the answer to our problem. Good, good. I will say that there is a little bit of subtlety going on here. It's not always obvious that we should say, oh, hey, let's just change the order of differentiation, or hey, let's try to plug things in early. But you should always be hopeful. I want to say the word suspicious. And when I say suspicious, you should be suspicious if things look terrible, that maybe there's something easy to go on. But I like to say the word hopeful now. If something looks like it's terrible, we have hope that there's a way to do it without doing it the long, terrible way. And this one was like, okay, we looked at it. Let me just make a quick note about notation. There's another way we sometimes write this. So this sort of looks like we're evaluating. We really haven't specified like which variable is associated with which entry. It's a little bit sloppy, and but the good news is we've been doing it for so long, we all have this sort of unspoken agreement. Okay, if things involve x and y, the first entry is x, the second entry is y. Another way you'll sometimes see this written is as partial squared z, partial x, partial y, and then there's a bar at 0, 1. So if you ever see something with a bar, that just means, oh, hey, I need to evaluate this, and so I'm going to carry out the evaluation. All right, well, that was our last problem. So it was a lot of fun. Thank you for coming. I hope you had a good time, and keep practicing. Get comfortable taking these partial derivatives. The more comfortable you get, the better you'll be. All right, have a great day.